let's look at using calculus tools to analyze a parametric curve. I'm going to go pretty quickly through a whole suite of tools and some geometric ideas that are related. So we're going to look at a pretty simple, a pretty nice curve. It's actually pretty deep, the analysis you can do with it. And it's going to be 3t minus t cubed for x and 3t squared for y. If you plot this on the computer or calculator, you're going to get something that comes in. I looked at the most central part of it. Comes in from the negative, far away. When t is negative, comes in far away in the first quadrant, and when t is really big negative, x is big positive. So is y, and then comes in, does some interesting stuff near t equals 0, and then scoots out when t is positive. That's where x is very big negative and y goes to back being positive. Notice that y is never negative because it's 3t squared. And notice it's got this loop here, and we want to really concentrate on the features of that loop and use some calculus tools to see the loop. If you want to know a few points very explicitly, maybe make this a little smaller even. Yeah, that's better. When t is minus root 3 is where it first goes to this one self-intersection right on the axis, and then it's 0, 9. It's easy to check that. Then it goes down here at the t equals 0. You're at the origin. It's pretty easy to check as well. And then symmetrically, as t goes positive, it does exactly the same things except flipped across the y-axis. So there's some nice symmetry there. You can get that all out of the equation, by the way. So let's see what calculus tools, what kind of questions we might have for this thing. Let's see. It looks like the tangent line to this curve is horizontal right when it hits the origin. Is there a nice easy way to show that that comes from the equations? When and where is the tangent line vertical? Looks like there's 2 points around here and around here where the tangent line is vertical. Exactly where are those points? And another thing would be, what about the slopes of the 2 tangent lines at the self-intersection? That's interesting. There's 2 times it goes through that point, and it's going in different directions. That is not something you have an analog of when you're looking at the graph of like y equals f of x. Okay, so the key to all of these questions, let me just put it up right here though, is to calculate dx dt and dy dt. We'll put those together in a combination in a second, but I want to tell you they each have their individual meaning. Dx dt is exactly, if you just keep track of the horizontal motion of this particle, it's just how much is it moving to the right or left and how fast. And so we would call this the horizontal velocity, or you can sometimes call it the horizontal component of velocity, because what we're going to do very soon is we're going to create the velocity vector, and this will be exactly the horizontal component of that vector. So we're going to bring in vectors into this story very quickly. And so it's good to review your vectors a little bit in preparation for that. Okay. And dy dt similarly is just how much it's moving up or down, and we're going to be identifying that with the vertical component of the velocity vector. Now, to just look at where the tangent line is horizontal, well, let's see. That's where you have horizontal motion. So dx dt should be non-zero, but dy dt should be specifically equal to 0, because you shouldn't be going vertically if your tangent line is purely horizontal. So this is going to happen. So horizontal motion is going to happen when dy dt equals 0, and you should check that dx dt is non-zero, because otherwise you're actually momentarily stopped. If you have both of them being 0, you're momentarily stopped, and weird things can happen there, because when you momentarily stop, you can go off again in a different direction. You get funky behavior. It's not super nice and regular. So let's look at this, dy dt and dx dt. Oh, well, let's calculate these. In this case, dx dt, remember, it's the derivative of 3t minus t cubed, so it's going to be 3 minus 3t squared. Let's put it right here. And dy dt is going to be just 6t. Okay, so here, dy dt equals 0. That's just going to be where 6t equals 0. And the one place that's going to happen is where t equals 0. Is it true that dx dt is not equal to 0 there? Yes, because dx dt is going to be 3. Okay, so yes, And in fact, it confirms that the only place where it's moving perfectly horizontal is only at the origin. That's what it looked like from the picture, but it's great to confirm that. Okay. When and where is the tangent line vertical? Well, that's very similar to this. It's where dx dt equals 0. But we better actually have it moving in the y direction, or else it's rather more complicated. So dy dt should not be 0. So let's set dx dt equals 0. So that's 3 minus 3t squared. Okay, so that's going to be where 1 minus t squared equals 0, or t equals plus or minus 1. Okay, so let's figure out exactly what's going on. What's going on with a y there? Remember, dy dt is 6t. Okay, so that's going to be where dy dt is plus or minus 6. Okay, that's not 0. And where is it going to happen? So very often with parametric curves, you're going to get everything in terms of t. The easiest thing to figure out is when something happens, but then you want to plug it back into the x and y to figure out where that's happening. So x and y, well, no matter whether this was plus or minus, 3t squared is going to give you 3. And if it's plus or minus, well, let's see. If it's plus, remember it's 3t minus t cubed. We're plugging in, let's say 1. Okay, that's going to be just 2. If I plugged in minus 1, everything would flip and I just get a minus. So it's going to be a plus or minus 2, 3. So I'm actually going to put in those points. Those are really interesting points, and I hadn't noticed them before. 2, 3, minus 2, 3. And t, when t equals 1, it goes through 2, 3. And those are naturally these points right here. 2, 3, minus 2, minus 3. And if I had t labels on here, if it was a better plotter, it would have minus root 3, minus 1, 0, 1, root 3, and then off. Okay, so that's cool. We've seen some good stuff. Okay, now let's go ahead and combine these. The cool thing is that so far I've only talked about horizontal or vertical, and that's allowed me to look at dx dt and dy dt independently. But the key thing of the next part is that if I want to get dy dx in general, I do exactly what this notation would seem to indicate. I just divide them and it looks like the dt's cancel. What's the proof of that? There's actually some really deep stuff behind that. I mentioned in class that at the heart of this is what's called the implicit function theorem. But for this level, it's just the chain rule. If I just clear the fractions, then I get dy dt is dy dx dx dt. That's totally true. That's the chain rule. Now it's interesting that temporarily I'm thinking of y as a function of x and x as a function of t, and then saying what would that mean about how y depends on t. It's a little bit weird because what's given here is just y is a function of t and x is a function of t. I've never actually solved for y as a function of x, and I'm not sure exactly how to do that. It's not super hard, but you'd actually involve some plus or minuses. This isn't really a function of x at all, right? This doesn't pass the vertical line test. But it turns out that locally, as long as I say just near some t value, this all makes sense. And I don't have to do any complicated solving of really funky algebra. I just have to divide. It's a very, very powerful statement. So in this case, we're getting 6t over 3 minus 3t squared, which simplifies a little bit, to 2t over 1 minus t squared. Okay. And now where was that self-intersection? At t equals root 3, I get dy dx equals 2 root 3 over 1 minus 3. That's minus 2 on the bottom, so you just get minus root 3. Let's check that sign. Remember, t equals root 3, that's positive. That's when it's on its way out to the left. That's coming up like this. And that's indeed where the slope should be negative. And the other one is just going to give me the opposite slope. If I look at t equals minus root 3, I'm going to get dy dx. The bottom doesn't change at all, and the top just flips sign, and so I'm just going to get root 3. Okay, so pretty neat. We've got some really good information there. So let me go back to this idea of velocity and take that more seriously. Actually, let me cut off the video right there, and we'll do in part 2. We'll start doing this idea of velocity and speed.